Think about your morning routine for just a second. You walk into a building, step into a little metal box, the doors glide shut, and you're whisked hundreds of feet into the air. Honestly, millions of us do this every single day without a second thought. We step in, press a button, and just expect a perfectly smooth, completely safe ride. It's one of those marvels of modern life that we kind of take for granted, right? We trust the gentle hum, that slight shift in gravity, and the familiar ding at our floor. But behind those closed doors,
what if the cable actually snaps? Just imagine that terrifying feeling of weightlessness for a fraction of a second as gravity takes over. That is exactly where things get interesting. Okay, let's dive into this, because that absolute nightmare scenario, that's right where the magic of mechanical engineering takes the stage. Elevators aren't just simple boxes hanging on ropes. They are highly sophisticated survival machines packed with an incredible system of fail-safes. So in this explainer, we're going to explore the invisible, lightning-fast mechanisms that are literally protecting you on every single ride.
let's start with Section 1, the mechanical hero, detecting the drop.
You see, before anything can physically stop a falling elevator, the system actually has to realize it's falling in the first place. Enter the Overspeed governor. Think of this as the brain of the entire safety operation. It's a completely separate, dedicated device that is constantly monitoring the elevator's speed. It has a very specific preset limit, and the very second the elevator accelerates past that limit, whether it's because a cable snapped or maybe just went a little slack, the governor immediately springs into action. It is the intelligent trigger that senses danger milliseconds before we would even realize we were in trouble. The actual catch is a rapid, incredibly exact science. Let's break it down. Step 1. The governor detects that overspeed. Step 2. That detection physically triggers these lifting rods, which instantly transfer the movement right to a lifting rack. Now, step 3 is where the real muscle comes in. Wedges, which are typically made of incredibly high-strength materials, are violently forced out to literally grip the rigid elevator guide rails. And finally, step 4, this massive friction brings the entire elevator to a safe halt. Basically, it's an immediate physical bite right into the metal rails. But listen, for that to work flawlessly, the synchronization has to be absolutely perfect. There are multiple components moving all at once here. You've got gear holders guiding the safety gears movement, plus jacking cylinders and compactors. But the real unsung heroes here are the connecting rod mechanisms. These rods are exactly what relay the movement from the governor directly down to those wedges. They make absolutely sure that the wedges on both sides of the elevator engage at the exact same split second. Think about it. If one side gripped even a tiny bit before the other, the whole car could violently twist. These rods guarantee everything happens simultaneously, keeping the car perfectly stable and aligned. Which brings us to Section 2, the science of stopping, the force of the catch. Now, what's really interesting about this next part is that stopping a heavy metal box full of people in midair isn't just about grabbing a rail, it is entirely about managing physics. Let's talk about the older, original style of safety gear, known as instantaneous safety gear, specifically the wedge type. When this particular gear deploys, it acts completely rigid. I mean, it bites down hard. The stopping time is an unbelievable 0.01 seconds. The stopping distance, just a few millimeters. But because it stops so abruptly, the car undergoes a massive, incredibly violent deceleration force. We are talking about an impact of 5 to 10 G-forces, sometimes even more. To put that crazy number into perspective, 2.5 Gs. That is the maximum instant deceleration a normal human being can comfortably withstand in an emergency stop. If a modern, fast elevator full of people suddenly stopped and generated 5 to 10 G-forces, the sheer impact would cause severe injuries to everyone inside and likely completely destroy any goods they were carrying.
So obviously engineers had a pretty massive G-force problem to solve if they wanted to build faster elevators. And thankfully for all of us, they did. You can breathe easy now. Because this is where the pure genius of modern engineering really shines. Progressive safety gear. While the instantaneous gear is rigid and abrupt and strictly limited to slow elevators moving under 0.63 meters per second, progressive gear utilizes something called elastic slip. So instead of a sudden bone-crushing jolt, it acts almost like a high-tension spring, applying a controlled, gradually increasing braking force.
Moving on to our final section, Section 3, a safe, smooth ride, engineering peace of mind.
This progressive safety gear allows the elevator to brake over a controlled slip distance. It actively absorbs the shock, safely dissipating all that dangerous kinetic energy. This controlled braking procedure completely minimizes the chance of passenger injury and prevents extreme mechanical stress on the elevator's own components. But, it all comes back to one absolutely critical point. As our source material states, understanding and maintaining elevator safety gear is crucial to ensure compliance with safety standards and provide peace of mind for passengers. This brilliant system of governors, connecting rods, wedges, and elastic slips, it only works if it is meticulously maintained. Regular, rigorous checkups by trained professionals are the final, essential human layer of safety.
We started this explainer by asking you to think about your morning commute, the incredible trust you place in that little metal box. So, the next time you step into an elevator, will you think about the invisible engineering that's actively protecting you? The overspeed governors quietly watching your velocity, the connecting rods waiting in perfect, absolute sync, and the progressive gears ready to catch you securely if anything goes wrong. It is a masterful, unseen symphony of physics, happening quietly right behind the walls every single day.